We are live.
Okay, everyone. Hello. This is another Wolfram Institute live science stream. Today, we are continuing our discussion
Live
with
science.
Carlos on sub-axiomatic foundations of mathematics. Now, for those of you who have watched previous streams, I've kind of made an attempt to provide a kind of high-level summary of this project several times. So if you're watching this, if you've been watching this several times, I don't want to sound like a broken record. So actually, I think Carlos, because Carlos is the lead on doing the research, maybe Carlos can provide a nice kind of summary of the kind of goals of the project and what he's been doing since we met last time. So Carlos, I mean, please go right ahead.
Absolutely. Thanks, James. So let me actually, before I share a screen and there's any visual information to clutter people's minds, I'll just preface by saying my understanding of the overall goal here is that we have one finding by Stephen a few months ago that you can essentially emulate Boolean algebra and other systems like arithmetic and things like that with SK combinators, and there's this particular way of implementing the way Boolean algebra works and in the way you do arithmetic just by performing some rewrite rules on an abstract system called SK combinators, right? So, so the basic idea here is that we take Boolean algebra as a good example of a non-trivial, interesting mathematical theory, abstract mathematical theory. For many accounts, this is what logic is like, and so it's the human understanding of reasoning and thought and whatnot. But otherwise, it's just some formal system that we think is sophisticated enough and interesting enough. And we look at it from the point of view of what we call the machine code. So we go down to this level of SK combinators, which, as you will see, is very user unfriendly. It's very hard for humans to know what's going on. And hopefully, I did my best to show the sort of surprising and counterintuitive features that this system has in the last couple of days that I've been working. And so the basic idea is that we know we have a very good intuitive handle on how Boolean algebra works, right? I mean, like, we know that false and true is false and things like that. It's something that is very intuitive to us. However, we have a very intuitive. We also have a very intuitive handle on SK combinator rewrite rules. The rules are very simple. We can just see, this is what it does. Okay, no problem. But we have a very bad intuitive handle on SK combinators multi-way rewrite systems, right? So we have very, very bad intuition on that. So my task in the last couple of weeks, since I've become fluent with the necessary coding and got up to speed with all the stuff, has been to essentially, in my view, has been to bring to the surface the more intuitive aspects of this non-intuitive realm of SK combinators, particularly emulating Boolean algebra. So what I will show you today is a quick summary of what the project has been, and hopefully you will see that the concept is quite simple. You don't require really any prior knowledge on mathematics that much. I mean, you just need to know what a machine does repeatedly and so on. And then we will get into the sort of hypothesis that we had last time. So what happens when, how many times does these operators appear in each other's emulations? And what happens when you have a ternary expression, for example, that involves more than one operator? And then hopefully we can discuss the new directions and things like that. So yeah, if you're ready, I'll share and I'll show you the stuff.
Yeah, let's go.
Okay, so this is the one. Can everyone see this?
Not yet. Yes.
Okay.
Yep.
Good. So anyway, so this is a quick summary of the stuff that I've done since the last live stream, in case anyone's curious. But let me first summarize what the functions that I've been implementing do. So basically, what we do is we attribute. So SK combinators are essentially expressions of two characters and brackets, right? So these are sort of function-looking expressions that involve just two characters, S and Ks, and different levels of applications, right? They effectively act as heads, so the Wolfram language deals with them very effectively because that's what an expression in Wolfram language is. So it's very ready to be processed by this particular language. But what we do is we essentially attribute a truth values assignment from true false to KSK, and then we assign similar expressions for the functions, the Boolean functions. So for this example, we choose and so we choose the evaluation of and on true and false. So you can see that the evaluation, so and is given by this expression. This is what Stephen found. This is what some people have known for some time, and then we basically use this as a head, and then we use a bracket and a bracket to sort of pass as arguments the corresponding assignment. So perhaps I could do it a bit more clearly here by writing. Oops. So if I write this expression, which is an obscure expression of what and should be, I will pass it to two new arguments that you can see here that are empty. I'm going to pass it, according to the assignment, the truth value of, true first. So this is true. And then the truth value of false. And you will see that you get that expression, right? So that's where that expression comes from. It comes from one particular expression, and then using two arguments, two sort of generic brackets as arguments. And so the magic happens when you take this as an initial step of a rewrite system, and then you have to determine some rules. So the two rules are the S and K rules. So these are independent from each other. And just involve what they see in their bracket structure, right? So S, 3 brackets, and it does something, and K, 2 brackets, and it does something, right? So these are the two rewrite rules that apply to combinators, to SK combinators. So in particular, if we take this initial state, oops, sorry, I just opened that window. If we take this initial state, and we apply this function that essentially what it does is it applies the change generically in any position that occurs, right? That any position that occurs, then we get this simple small multi-way system, right? Eventually, what's important here is that eventually we get the final state being SK, which corresponds to the truth value false, and therefore it sort of closes the loop on the emulation because we have that true and false equals false, and so the emulation is complete, right? So that's the core of what's happening here. I haven't really developed anything beyond this other than including maybe hierarchy later on, and we'll discuss this exactly how to do it systematically. But what's important is that obviously we have a wealth of Boolean combinators, Boolean operators, and the idea is, by a systematic search, you can find them all, and this is the list. We have this association that just gives you all the combinator representation of your Boolean operators. So the idea here is this is all the stuff that we can get into later. Okay, so let's just see some of these functions, and this is recap from last time. Let's just see how they operate. So basically, you have this is summary for true, false, false, true, false, false in terms of arguments, and these are just the multi-way graphs that you get out of the SK combinator rewrite system, right? This is an extra piece of data that I thought was interesting, as we discussed last time, and I'll leave this for later because this might be relevant for something at the end.
Okay.
But basically, what you can see is that and this is the combinator flavor of and, or this is the combinator anatomy of and, right? Because just truth value application, this is what and looks like for combinators. I'll just review because all this section shows is the topology of the multi-way systems. You have tooltips. You can look at the states if you really want to. So different functions, especially if they are of different length, they have very different multi-way systems. These graphs represent which are isomorphic. So although they look all similar, they are not isomorphic. They're only isomorphic in this pattern. So you want to see a few more. If my computer doesn't crash for graphics, okay. So you have this equal, for example, that doesn't have any isomorphy, etc. So this is the stuff we did last week. So there's many questions that are raised at this level, right? Like, so just at this level, we have questions such as, okay, what are these intermediate states? What's going on between going from an initial state that we know what it represents in emulation? We know it's a head and then a pair of arguments in which we just insert true and false in whatever pattern we want. And we know that at the very end, we're going to get either true or false. But we have no idea what happens in the middle. So the entire effort that I'm doing is to try to understand what's going on in the middle of this particular multi-way systems and some other more general ones that we have to discuss exactly how to parse them, because it's a wild west of possibilities. There was an interesting, so just to show the topologies, this is the simple one.
Yep.
SOAR was quite beautiful, I think. There's only one symmetry, and I mean these two look almost isomorphic, but they are not. These two are isomorphic. NOR, I think it's more complicated. Again, only one isomorphy. Converse was very short. It was this rewrite system that just was straight. Not converse, I think, was quite long as well. Well, yeah. And NAND, which is important because we can always just rewrite everything in terms of NAND. No isomorphy between the evaluations of NAND. Okay, so the first thing that we asked last week was, to what degree do the intermediate states involve the states that actually encode or emulate the Boolean functions? So for that, I've done some functions. So I have, okay, so let me recall operator legend. So these are all the emulations, and I have a color code. So color legend. So I've chosen some colors to code each of the emulations. So in this first one here, and this is just AND, it's a simple one. The only thing that you should spot from above is that the initial state is purple. Should be purple because it's detecting AND in that position, right? So this is a bit like last week. But then the interesting one, okay, so this is the other one. So what this is detecting, I should say, is that there is an AND expression in the first state, right? What this second one is detecting is, so the difference between this is evaluation all motifs argument, and this is evaluation of all motifs, right? So what this is detecting is that there is an AND function motif in the first state, right?
Yeah.
So including the brackets. So the function that I really fought this week to get done is to identify the actual states and be able to visualize exactly where the different Boolean functions happen. So these are the two. Well, only the expression or the function with the brackets, and you can see that they basically happen in the same places. So this is so just to understand what's going on here. So this is detecting in the evaluations of AND. So this is a table of 4 lists basically. To understand this, maybe you can suggest some quick editing or layout. But basically, the way you read this is a list of quadruples. So you have basically the four evaluations in a list, and they
make it a grid.
A grid?
Make it just
Can I
just apply a grid function.
Like this?
Yeah.
Just like that?
I think yeah.
Ah, okay, excellent.
Yeah.
So yeah, much clearer, of course.
Yeah, thank you, Nick.
Yeah, I was hoping that Nick will suggest something very quick, and that was indeed the case. So anyway, I'll apply a grid here as well, just to show you the point. So so basically you can see that where the detection of these states here is detecting just the expression that corresponds to the emulation, whereas here is detecting, okay, it's encircling also what's inside, but really you should look at the leftmost expression, and then it detects the expression and the 2 arguments that are generic. It's not detecting the fact that this is a k. It's just detecting that there is something in 2 brackets, right?
Yep.
So a reality check is that there is no distinction between these detections and these detections, right? Here, 1 hit, 4 hits, however many hits, these are the same. So it means that in this case, all the instances of AND that happen within the sort of machine code, the combinator machine code of AND, is really just AND not being rewritten, right?
Yes. Yes. It's just a delayed. Oh, I don't want to say delay because delay is some other term, but it's
Yes.
just a kind of the evaluation of it just doesn't occur for a while.
Exactly.
Yeah.
Exactly. So basically, yeah, it's applying to somewhere else, and the moment it gets applied, it disappears, right? Okay, but it gets much more interesting than this.
Okay.
Don't be disappointed by this behavior.
No. This is the boring example against which we contrast the interesting one.
Yeah.
Right?
Yeah.
Okay.
Exactly.
Yeah.
So, or again, here is just detecting the motifs that happen within it. So we get a red hit at the top. Maybe make it a bit bigger for the stream.
Are there any other colors
No.
besides the red? Okay.
No. And we will see explicitly in the list now. So.
Okay.
So yeah, so there's nothing there. So only in the first one, if we search for arguments, only the first ones as well. I mean, that's a good reality check. That's what should happen. And then when we actually have the list, if I do the grid thing, it's exactly the same phenomenon as before, right?
Yep.
I should do it here. Yeah, same phenomenon.
Yep.
Okay, so funnily enough, and or, which are basic logic functions, are boring in this sense. I should say, boring in this sense is kind of a good thing, meaning that they are kind of fundamental in combinator landscape, right? Like they don't really go outside of their own sphere, right?
Well, right. If we found like random XORs or implies or something showing up, I would basically attribute that to coincidence or something.
Yeah.
It would be very strange to see them, right? Yes.
I would even say, there probably is some kind of problem if we found them in those two. But anyway, but that's just my intuition. Okay, so now let's see some interesting ones, hopefully. Okay, so equals sounds very basic.
Okay.
If my computer allows me. Oh yeah, so this was this interesting one, right? So this one is showing already the states. So the coloring happens, it only shows one color. So it only shows some of the...
I see two.
Say it again?
Blue. I see two colors.
Yeah, it's blue and magenta.
Blue and red.
Yeah, blue and magenta in this one. Yeah. You will see in the list. In the list you will see explicitly. No problem. You don't have to squint to see this. So the point is we get two colors here. We just get this impression of, okay, these are the one of the issues that you might think about is that so one of the lessons, just to hammer this home, one of the lessons from this is that the moment that the head gets rewritten, right, the entire motif disappears, and then it's just combinator evaluation, combinator rewrite all the way through until true or false, right? In this example. So this is what you might expect is happening here, right? You might expect that you go from something that contains blue and then it just propagates because it's not being evaluated. And this maybe changes it and then it propagates until it's getting evaluated, right? So in order to prevent that, I wanted to check with arguments, because if you check with arguments, then you can tell it's not just a random piece of S and Ks, but it's actually that there is a whole function that is not being evaluated. So when I do with arguments, we get this pattern, which is not exactly the same, as you can see. So these are different, right? So you can see that there's for example, all these states have no pattern inside, and then suddenly there's a blue pattern, and then here there's a magenta pattern, and then no more patterns. And similarly here, patterns happen halfway through. Anyway, so I think the full story, I should show you the kaleidoscope of all the occurrences that happen in the actual list. And so here's the list of occurrences.
Can we make that a grid too?
Yes, let's make that a grid.
Okay, well, so what are we looking at here?
So this is, in my opinion, a lot more interesting already.
Well, let's take a look at this then. So well, it seems as though if we take like the second column, for instance,
Yeah.
it seems as though eventually we have evaluation that eliminates the purple. What's the purple function?
I mean, I'm just bring that. So that purple is equal, and we
Yeah.
are
Okay. So
we're
okay.
at equal. Yeah.
Yep. Okay.
Yeah. So it's
So
the
eventually,
outermost. Yeah.
yeah. So equality is not evaluated for a few steps. Then it is, and then we still have three others. So what's the light blue is
Light blue is not last.
not last.
Magenta is implies, and pink is true. By the way, this is not checking for first and last, because those are just true and false for in the code.
Well,
Because otherwise it will highlight everything.
but what about true and false?
True, no. So true and false. So first and last are the ones that are just k and sk. True and false are
Yes.
the constant functions true and false, which have, I mean, sure. So false has this expression, and true has this expression. These are non-trivial.
Got it.
Non-trivial expressions.
Got it. Well, where are not last, true, and what was the other one?
Must be
Uh,
true and not last, and magenta is implies.
well, so these are surprises. These are surprises. We didn't expect these to show up, and they do show up.
Yeah. I mean, actually, this is. I mean,
But they do
we now
show up
have,
in the. But
Yeah, go on.
yeah, go ahead. No, go ahead.
So we have now the full function that detects everything, but actually we could have known this from just inspecting the expressions, because these expressions are. So if you look at this, these nested expressions, they just happen on the head, right? So
Yeah.
so it means that when you actually look at equal here, this expression here has all the other
Yes.
expressions inside, right?
Yes. I mean, They're not appearing in the immediate states. We just happen to begin with them.
Yes.
I mean, this is slightly more interesting, but it does seem as though essentially we begin with some statement using equality that also happens to contain these other operators as sub-expressions, and that progressively these are evaluated away so that we drop some of these colors as we go down, but nothing novel is fundamentally appearing.
Yes.
This is mostly just a kind of a strip down with more of these Boolean functions.
Correct. There is a little
Yes.
kink though.
Okay.
Here, right? Although
Well, it's getting shuffled around a little bit.
I
Oh, and it's
suspect,
getting duplicated.
yes,
Yeah.
but this duplication is because S duplicates, right? S duplicates, so I think the intuition here is all good, right? Now, this is matching the expressions, right? So let's match the functions. Put it in a grid. Oops, no. So things become much more interesting when you actually match the functions and not the expressions. Because the functions is really what the emulations are, right? The emulations are not the expressions, are the expressions applied as two-argument functions. But it's essentially the same pattern, right? Because if you don't have the function inside, you can't, I mean, you're only going to recover the shape of the function. I mean, these two are related, obviously. Like you only see the outermost
Yes,
expression.
exactly.
Right.
Right. Yep.
So yes, this one more interesting, still not mind blowing, right? In my opinion.
I agree. Yes, I agree. Right.
Okay, let's see what happens with implies. I don't really remember exactly every one of them, so let's go grid. Very similar, right?
Yeah.
And in this one, is this the right one? Yeah, this is the right one. If I do evaluations, all motifs, no, all motifs are.
But wait, can you remind me why it's so repetitive there? Like all the columns start exactly the same and no changing at all.
You
What
mean,
exactly are you doing?
I imagine it's because it's keeping it, like it's only applying the function to one column at a time. So it's just an artifact of how I think how the list is presented. Because I have the four. I think it's just the way I apply the function, which basically goes through the first list and then through the second list or something like that.
So you're saying we take the first column, we hit K, and then you can see the next step later, you begin to evaluate the second column, which is remain unevaluated until you hit K in the first column. Then you hit K in the second column, and then the next step afterward, you first begin to evaluate the third column, and
That's
eventually
right.
that hits S of K, and then the next step after it, the third column hits S of K. Yeah,
That's right. Yeah. That's
it's
right.
probably
So
it's probably a better. It's probably a
basically you
it's probably,
operate on the whole table, right?
there's
On the whole
probably a
proof
way to do
table.
this. There's probably a way to do this where, I mean, on the one hand, you have the nice feature that they're all of the same, like there's the same number of rows for each of these, where if you did it differently, there wouldn't be. But you could probably do this in a way where you're not repeating the K's at the end or S of K's at the end,
Yeah.
and you're also
Absolutely.
not and you're also not repeating the initial expression.
Yeah. For sure.
Yeah.
I mean, this was.
Yeah.
I wasn't even thinking about the grid, and of course, I mean, this is. Yeah.
Yeah, sure. These are basically presentation
Yeah. Just
details.
cosmetics. Yeah.
Okay, well seems like another example where fundamentally we begin with some expression and gradually the 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 Boolean operators are lost, and they're lost,
Yeah.
one at a time. Okay.
Okay. So
Okay.
next one. Right. So this
Okay,
is.
come on, XOR. Come on, hit me.
Yes.
Hit me.
Okay. So.
Come on.
So XOR. Let's
What's
go.
this?
Okay. So this is getting more interesting.
Okay, yes. Yeah, this is,
Okay, so we have the lone. We have the lone. Who is this guy? I think this guy is first or something, or true or something. Or let me see. Who's brown? Oh no, last.
True.
Oh no, that's not. No, it's
False.
It's false. Yeah. There's the
Or
lone.
not convert? I can't tell. Yeah.
There's the lone false that just appears there, and then we have all these. These greens are not first or converse, maybe converse. Can just check with the handle. It's not a problem.
Or you should have really just added some tooltip when you highlight.
Yeah, I agree.
Yeah, that's another good idea.
Yeah.
Yes. Yeah.
You can just add tooltips to on top of expressions.
Well, Nick, do you mean like you would drag your cursor over it and it would just tell you what it is? Like it would tell you that it's false or implies or
You're already using the legend, so you know when you're highlighting which one of those it is. So you just put it in the tooltip.
Okay, yeah, I mean this should be very easy to implement.
You can do it right now.
Okay.
It's not gonna take you a minute.
Yeah, tell me. So how do I do it?
You have this highlight function, I remember, right? Just scroll to that highlight function.
It's been modified a little bit since you saw it, I think. But let's see. Because what I do is
When you have frame, basically, where's your frame?
Okay, yeah. So it's in here. Yeah. It's in the first one.
So you can just around this frame you can say tooltip.
Okay. Let's do that.
And put your operator there too as a second argument.
Okay, so what do I pass? Just gonna open this info for my.
The whole frame is gonna be the first argument, and your operator is gonna be your second argument. That's it.
And I pass operator?
Yeah.
I guess. Sure. You think it's gonna work?
Yeah, why not?
Yeah, let's try. Yeah, I agree. So, let me just close this section. Yeah, I'll close this. So let's try it here. Yep, that worked.
Great.
Excellent. Yeah, Nick's wizardry at play, everyone.
Yeah. Just learn all the 6,000 functions of the Wolfram language.
Okay, so let's go back there and let's reevaluate. So where are we? This looks very neon.
XOR.
This particular region looks very cyberpunk. This region is a little bit more lively. I don't know. Okay, let's go. Okay, yeah, so this should be all XOR, and this is converse.
Converse. Weird.
This is true. It's converse, and this is false. Yeah.
Okay. What about in these other columns? What happened?
So I think it's similar.
Yeah.
Because these are so similar, right? So we have to scroll down because this is all redundant. So the top is quite similar. The first and the third are quite similar here. It doesn't have the random false. I think that's, wait, is that in the graph? No, you can tell from the graph. But yeah. Anyway, so yeah, this is the XOR. I think is the first example of non-trivial.
Yeah.
Non-trivial
Well, so
occurrences.
one quick thing to do though is, okay. So part of the reason why the converse shows up is because it is inside of that XOR expression. If you just eyeball it, so I could even, I could do this here. Let me bring out a little pen.
You mean last?
Here, let me just hold still.
Yeah.
I'm gonna show you something. So this, see that right there?
Okay.
That I just underscored?
Yeah.
That's the same as this.
Yes.
Yeah.
Yeah.
So this is another example where I'm less surprised to see. We could even follow this. So what happens here? So we lose XOR, but we happen to keep this still
Not quite the same.
under evaluation, and then eventually it shows up here.
It's not the same, James. It's not the same actually.
Is it not the same?
No, there's an
If
extra
it were the
bracket.
same, it would highlight it. It's like
It's not
it was
exactly the
highlighted.
same.
Oh, you're right. It's different by one bracket,
Yeah.
right?
Yeah.
This little bracket here.
Yeah.
Okay, well, okay, so that might be where it. Okay, why am I bringing this up? I'm trying to one thing that's still not clear is whether or not every once in a while we just happen to get lucky, or there are just these kind of contingent effects where you happen to have some sub expression in one of these Combinator emulations of Boolean expressions, where under the rewrite, this sub-expression happens to get transformed into something that just happens to match something that we recognize.
Right.
This is like, the jury's out on this still, right?
Yeah.
Which is right now I think the first thing that we're testing for, which this XOR example shines some light on, is, is it the case that when we evaluate these, all we find are our initial expressions, eventually getting dissolved in the kind of machine code, which is what you see for and or and these other ones, right? That's kind of case number one,
Yeah.
which is you begin Boolean and eventually that just becomes dissolved. This case is XOR becomes dissolved, but then there are these other Boolean operators that show up. And the question is that just a kind of is that just an like a computational contingency where it just
So we
happened to be
don't know
a
that
slight
those are not Boolean operators, right? Because you just because you only have a single table that you're comparing it to. You don't know whether those sub-expressions, when there's no highlighting, that there's no Boolean operators there at all. You have to compare their Boolean tables, what Boolean tables those sub-expressions generate, and you can say whether they're Boolean or not. That would be the proper way to compare it, not just to the single table that we happen to find.
Well,
Yeah,
Nick, you say this like every single time we meet, I think.
Well, yeah,
And but Nick, I mean,
I think that's
if we're comparing it for just all possible Boolean operators that can be emulated by combinators, I mean, feasibly, many of these will be. But the question is,
of course.
under our particular emulation, are those ones relevant?
What do
Yeah.
you mean,
I
our
mean, they're
particular? Well,
I mean, Nick, I agree with you that the complete search would be with all of those. If I had access to like a systematic way to generate emulations, like Combinator emulations of
you don't have to generate them. You just there you have it. You only look at those sub-expressions that appear there, and you just check those sub-expressions for their Boolean table. Right? You don't have to generate all of them and then make a giant
I see
table.
what you mean. I
Boolean
see what you mean.
operators.
Yes. So I think, James, I think what Nick is saying, if I understood you correctly, Nick, is that you use all the expressions in this grid, right? In these tables, and then
Yeah.
you search for those as well in the others.
Yeah, you only search for those sub-expressions that appear
Yeah.
there, not for all. For all that you can enumerate.
Yeah, actually,
Right.
I'm gonna come back to this point later. So I'm gonna address your suggestion actually at the end of what I've been doing. So for now, let's finish just
Okay.
charting
Okay.
the different possibilities. So let me just highlight that this one I did the same thing but detecting for arguments, and I think it really it highlights much better what that this XOR is the first one that is somehow not trivial in this sense, because I mean it begins with this one, and if it doesn't detect the pattern, by the way, before when you said that this pattern actually happened there, it couldn't have happened because it would have detected it. That's what the function does.
Right.
So
Right. Fair enough.
it just
Yep.
occurred to me, but I think this particular view of the argument version of the function is much more clear because it basically tells you, well, we start only with blue, we go for a while, then suddenly green, we go for a while, then suddenly green, and then orange, and then we evaluate, right? So I think that's a much better representation of this non-trivial occurrence of sub-axiomatic dependence, or whatever we want to call it. And so, Nick, by the way, this is just a more of a technical thing that maybe we can discuss later, but I'm kind of mystified by why am I seeing. I'm sure this is to do with how the multi-way and the fixed point algorithms work differently, but I'm somewhat mystified that I'm getting a hit for orange here in the fixed point list, but I have no orange vertices in the tables. My only guess is that they will happen together with the green, but then I guess they should show up together with the green.
Just some kind of bug, I don't know. You have to investigate.
Okay. Yeah, I mean,
And
this
just
mystifies me. I think it has to do with how the fixed point algorithm works. That always does the thing to the left or whatever.
No, we still have to that expression, orange expression, still should appear in the multiway system anyway.
It should. Yeah. So it's
Yeah.
yeah. It's weird that this is anyway. I mean, to be honest, I was focusing completely on the actual expression matching this time, not the multiways. So the multiways are just a visual guide.
One possible naive question is you have these multi-way evaluations that you're showing above, and now when we have this grid, presumably each of these corresponds to the different multi-way systems for true true, false true, true false, false false. But of course there are different paths in each of these multi-way systems. It might not be the case for any of these, but it might be the case for some more complicated example that you have different paths within the multi-way systems that reach different states, or that have different intermediate that have different Boolean, say, operators in the intermediate states. Like if you look at what you have on the left here, right? There are actually many different evaluation paths that you can pick.
Yeah.
Yes?
Yeah.
Yeah, but then when we look below at the grid, presumably this is just one of those, right?
Yes.
Right. Yeah. Right. So at some point, when you have a more interesting multi-way system, you might need more than 4 columns in your grid, or you might need something else, because there'll be multiple paths that might be non-trivially distinct.
No, for sure.
But I think now it doesn't matter.
I think that there is some bug because remember last week we were, I was still unsure exactly how to make the vertices colored and this kind of thing. So there might be some bug at the level of coloring the vertices here, but obviously so these columns here are consistent with these expressions, right? Because the matching is like these ones. So you can see that. Let me see. If you go, notice how you start from blue. There is always a gray one. Let me make it bigger.
Yeah.
Right. So there's always a gray one. So I think that the path that the fixed point algorithm is taking is first here, then where, then gray. Well, not that one, but the one below. Then you see pink. Like why is pink? Probably because pink is inside the green and the green is applied later or something like that. And then you go all the way with some color, right? In this one, you have color all the way. This is a single expression, by the way. You have color all the way, and then to the point where there is no color here. So that's the final. So that's in here, right? When you jump.
Do you have an example where it actually overlaps or not?
Sorry?
Okay, is there any motifs that overlap?
Yeah, we had examples before.
And you should put this highlighting on your tooltips too, for your vertices.
Right.
Also, like these tooltips, like inside of those tooltips, just make this highlighting.
Yes. I think we discussed that last time.
Yes.
That would be really helpful. Yeah.
Should we do it now?
Okay.
There's more stuff to show, and I think more interesting.
Let's just, make a note of that. That's an obvious, little, again, another presentation illustration enhancement to make. But let's keep going with the results.
Okay, yeah. Let's go.
Because you were very excited before we began this call, so I presume that we haven't seen anything yet.
There's something quite cool. This is one of the 2 cool things that I wanted to show. But there's another cool thing that I'm eager to discuss with you. So what is this? This is the arc one, whatever. Just for tidiness. Okay, Nor. So this is one of the interesting. So let me see.
There's another.
So this was quite interesting in that this is the one that had these 2 states in the middle.
But where are they?
For some reason, it's not being picked up. There's some kind of bug here. Like there's some kind of
Well,
bug.
but again, another question is, this is a multi-way system. Is it the case that all paths actually reach those?
No.
Because it could be the,
No.
yeah, right,
Exactly. It's not a bug. It's
right.
not a bug here. It might be a bug in the coloring. That's all I mean. That because
No, Carlos, what I mean is, if you take the leftmost column in your grid, you're just taking one particular path
I understand.
down your multi-way
I
system.
understand.
Yeah.
No.
Okay.
I'm saying.
Yeah.
That's what I'm saying. What I'm saying is that these are pink, and there's no pink in the graph. That's what I'm saying.
Well, there's also that.
But
There's
that's
also
the bug that we were talking about before. We'll fix that. That's just like it's a coloring function that is not up to par with the sophistication of the actual motif detection function on the grid.
So it's the multi-way.
The multi-way
Coloring
works
is wrong.
good. The multi-way works good. It's just the coloring of the vertices.
Yeah.
I mean, the syntax somehow is not. It's a bit buggy for what we wanted to do. So.
Well, that's interesting because we were quite fixated on those two, vertices last time, and it turns out that that coloring those pink states are actually more pervasive than we might have suspected. Interesting.
But these are not the same. So this magenta is not the same as this pink because I think. Let me just bring.
Oh.
Yeah. So exactly. So true. This is true. And magenta is implies.
Oh, well.
So this is very.
So
This is one of the. It remains interesting. It was interesting last time, and I think it remains interesting, because there is indeed an occurrence of implies. Actually, Did I evaluate with arg? I don't think I evaluated with arg.
But one thing, Carlos, is functionality-wise, are you able to take different paths along your multi-way system and show, this kind of motif detect Boolean evaluation function for those? That's an obvious. It's an obvious because I don't know. Like Nick, do you know, for instance, let's say you just take some particular evaluation like we have in this grid. Is it like the leftmost, outermost? What is the which particular path are we taking from the multi-way system?
Well, that's arbitrary. You can just say it from the multi-way graph.
Yeah, you cannot tell from the multi-way. Like, I guess you could. I mean, I don't know.
There's no default.
Path?
Well, we can highlight the path there, obviously.
Yeah, we can.
Yes,
yeah, of course.
But it's not chosen random. It might be chosen arbitrarily, but it's not chosen randomly, right?
No, it's consistent. It's always the same. Because it goes to the leftmost, whatever. It has some arbitrary leftmost
exactly.
or rightmost.
So, so just as if you take this as an example, I mean, the leftmost path, it doesn't hit those magenta states necessarily at all.
Yeah. That's why we don't see them here.
Yeah, right.
That's why we don't see them. Yeah.
But those are, that's a kind of an interesting example of something that crops up. Well, so I think one lesson here is if we don't necessarily trust the coloring for the multi-way system, and we're only getting individual paths in these grids, then, I mean, two things, right? One is mending the vertex color for the multi-way system, but also showing these other paths, because it might be the case that there are paths that are funkier than the ones that we're examining right now.
Oh, of course. Yeah. Absolutely. Yeah. This was meant to be as a sort of an illustration of the functionality, the basic functionality, to then, because I mean, just getting the function to do what I wanted to do, it took me a long time.
No, I know. This is an iterative process.
Yeah.
But
anyway,
as colleagues, right, we have the responsibility to point these things out, just because these are the next steps to take.
Yeah,
right?
yeah, absolutely.
Yeah.
Anyway, just another lone orange.
Yep.
I kind of grew fond of this lone orange just showing up. Anyway, so let's just see. Okay, this one's not that interesting. Some other lone oranges.
Yeah.
These just look. What's interesting as well is that they all have their color identity because they have a mixture of colors, and it's a different mixture for the different operators. So I think this is very straightforward, like the first ones.
Yeah.
Right.
Yeah.
Okay. Then NAND. Okay, NAND is, I think, was interesting as well. Oops, that was the wrong evaluation. Yeah, I think NAND is actually interesting. But I don't want to run out of time before we. Oh, no. Oh, yeah. I should definitely show the last one. I don't mind staying longer, but yeah, NAND. Wait, this is NAND. Yeah. Yeah, some interesting stuff like this orange happening here. Yeah, happens everywhere, not there. But it happens in the ones that are similar. Right. So I made a note. I'll fix this so we can have the tooltips on the multi-ways as well, and we can get the full picture, and then I guess, because I was just wondering when you said choosing the paths, it would be great to be able to specify paths. I'm sure Nick knows how to do this, so I'll work with him to get this done. But I'm sure there's some function which you click on the graph, and then you can choose that as a vertex, and you can extract that as initial state. Is that possible to do?
Sure. Yeah.
Okay. Yeah. Anyway,
it would be fun if you could take the multi-way system and you could click on a particular path and it would just give you the evaluation. That might be a little more advanced, but wouldn't that be pretty slick?
I'm happy to slowly build towards that. I mean, that would be a great function, because that function will be very general. I mean, not just for this application, it will be a very general thing to have.
Actually, you're right. That would just be a good thing for multi-computation in general, which is click a path, get the single way evaluation for that path. Yeah. Overall, that would be a good.
Exactly.
That would be a nice piece of functionality.
Exactly.
Okay, so.
Okay.
Yeah.
Some comments or questions. So we don't run super late, but some comments or questions about just the evaluations before I move on to this more general expressions or hierarchy or whatever. You have any?
Well, I mean, I would say really the key question that we're trying to answer in general is what the correct interpretation is for these intermediate states. So we see examples where effectively you begin with some Boolean expressions and kind of progressively they're just kind of dissipated into just combinator evaluations. We do see examples where these other Boolean operators crop up. So I would say, really the first thing to do is probably just to make the fixes to multi-way system and to examine these other paths. And I presume also to do it with these higher arity cases, which are slightly less trivial. And I mean, just to accumulate this kind of corpus of experimental results, it seems somewhat premature. Like I don't think we've seen enough complicated examples yet to really understand what's happening, because we're taking very elementary examples.
Yeah. So
trying some more complicated examples. I mean, even with just arity 2, you can do things like true or false and true equals. You can do
right?
more complicated ones, and trying to, because I don't know, in terms of all the Boolean expressions.
Yeah, James, I'm getting there. I'm going there. So.
Oh, okay. Okay. Then let's keep going then.
Yeah.
So that's fine.
So let's save that discussion to the end, because that's what I wanted to get from you guys.
Okay, I'm ready.
Because I mean, this is a very simple one, but just to illustrate. So I was trying, and by the way, we don't have time now, but I was not being successful running proofs and so on. But basically, I wanted to illustrate something. I just wanted to illustrate. Okay, we now have this implementation of Boolean algebra in combinators.
Mm-hmm.
We know we emulate it by evaluation. We don't emulate it axiomatically. We emulate it by evaluation, which is equivalent mathematically, of course, but computationally it's different, right? It's a different thing. So the question is, okay, what if we actually, I mean, we claim to be doing sub-axiomatic foundations. So what if we wanted to actually go below the axioms explicitly, not just in principle or formally, but explicitly below the axioms? So anyways, you could have some implementation of Boolean algebra, and I tried this one. I don't think it worked. I think this one worked here, but for some reason this was copy pasting and it was not working for some reason. But anyway,
Because you have a column there. Why are you passing it as a column? List of axioms.
Oh, because this has the column. Okay. There you go. That's part of the definition, right? Okay, yeah. That's... and then I should say this. Should give the same, right? Oh well, or this, yeah. Anyway, okay. So
problem resolved. Okay.
So it's a very trivial statement. It's just saying that and is a symmetric operator, right?
Yep.
So what I think is interesting to think about, and this is something that is really up in the air. I mean, I don't think there's any. We don't gain anything from going more complicated from this level until we have a clear mind about this level. Meaning, what is the connection between the fact that these two are symmetric because these, there's the same argument twice. There's nothing to say there. But somehow, this system knows that evaluating true and false and true is going to be the same, right? Very interestingly, for and in particular, these two graphs are non-isomorphic. So if you were to just give me the multi-way systems, right, there will be no way to immediately tell that this is a symmetric function. Now, obviously, because we are defining it only on truth values, then it's symmetric by definition, right? It's not an axiom that this function is symmetric.
Right.
But anyway, I was bringing that up because, I mean, this is just to make the point. The interesting application is below, but I'm bringing this up because you have the possibility of somehow characterizing a behavior that is axiomatic for the operator, but it's somehow just random computation for the combinators. So actually, will this work now? Nope. But because I didn't pass Boolean logic, maybe? No, it doesn't like it still. Anyway, so this was just associativity for and, right? So and associativity is an example of basically the smallest thing you can put together, right? I mean, we can look into the error here later if we want to. This was just for illustration purposes. There's nothing there. So here's the thing, right? So let's try and emulate and associativity, which is basically the smallest expression that is not just evaluation, right?
Yep.
So in one example, right, there will be many combinations, but in one of the combinations you can do true and false, or true and false and true, right? So these two are expressions that you're gonna get some combinator expression for under the emulation, and so that can be done explicitly. So this can be done with Nick's function, or it can be done explicitly. And I'm just showing here explicitly, so everyone knows what I'm doing. So all I'm doing here, you can parse this expression, and you will see exactly this structure. But I'm just replacing and for the Boolean operator of and, truth value of true, truth value of false. So this is just the emulation of the left hand side and the emulation of the right hand side. These are the two expressions.
But what about the emulation of their equality? You could do that too.
Sure, but this equality is not logical equality yet. This is equality under our scrutiny, not under the formal Boolean system. Because, I mean, you can take, I mean, this equals here, I don't know, you see it as equals or as an arrow, I don't know. I mean, maybe I shouldn't write an equals, otherwise it looks... that equals there is just that you evaluate these things and
Oh, I see. Okay, you want to evaluate these two things to false.
Yeah.
Yep.
I mean, you could definitely state that as a logical phrase, right? But what I'm doing here is
honestly, I'm just saying that because I have a kind of an appetite for these more complicated expressions, just because I want to see what they look like. But
I know.
Maybe one step at a time. One step at a time.
Exactly.
That's fine.
Exactly.
Let's start with this. Yeah. Okay.
I mean, I know it's fun to do this larger stuff, but I think it's better to go to the larger stuff.
No. Go ahead. Okay. Look, this is more complicated than what we've been doing before. Fine.
Yeah.
Okay.
Yeah. So this is basically the smallest thing we can do in the next level, right? It's just
yes.
taking the third argument. So these two expressions, reality check, are different. And so we can evaluate them. So we evaluate the first one. Here the color code is basically the same as before. So we have some initial state, and we have black, false. That's what it should evaluate to. So okay, reality check, it works, right? It does what it's supposed to do.
Yeah.
The left-hand side evaluates to false, great. The right-hand side evaluates to false, great. Right? Okay, so here's the question now. So this is the first time that I'm actually directly manipulating, having access to these ternary expressions now. So basic question is, okay, how are these related? These two multi-way systems, right? Because they seem to be independent. I mean, they work independent from each other in principle because they just run the initial steps. The initial states are different. So one thing to check is, are they isomorphic? They are not. Obviously, I mean, it's visually clear they're not isomorphic.
Yeah, it's somewhat hard to tell, but okay.
It's not hard to tell, but yes, they are not isomorphic. And then the next question is, okay, do they share some middle states, right? And interestingly, they do, not just the final one, because the final one they have to share, but they share a few of them. Here they are. And okay, so I suggest we put them together. So we create a bigger graph that just has the two initial states and it has the final state, right? So basically we combine both graphs.
Are you going to union them?
Yes,
or
basically union
intersect them
and highlight the relevant stuff. So here's the result, because we are short in time. Let me just show you the result. So this is the result.
You can also try for subgraph isomorphism search.
Subgraph.
Maybe one graph is subgraph.
You could check that. Yes, you could check that as well. But I think in this case the pattern is quite clear just from the shape of it. So yes, so blue and red, of course, right and left, and then the intermediate states are yellow, right? So here you can see the coloring is yellow when intersect vertex list is there, right? So I thought this was quite interesting because you have these two emulated expressions, blue and red, are the emulation of the left-hand side and the right-hand side, which are essentially the two terms of associativity, right? The axiom of associativity. And so they get emulated. Okay, they get put some values and then emulated because we are doing value emulation. But then they flow, and they eventually, I mean, in some of the paths, you can certainly choose a path for which you land on a common vertex and a common state, and from there you flow necessarily to the end, to the.
So this is an interesting way of showing that they're equal. You didn't set them equal to one another. You just ran them both multi-computationally, and they tend towards the same fixed point.
Yep.
Do you know what these intermediate states, though, they're given the same color, but they're are there Boolean operators in them, or are they just random shared combinator expression?
I mean, let me just use the functions that I have.
Yeah.
How do I do this actually? Wait, let need to know.
Basically, it's just a few last steps, maybe.
No, but I'm just going to apply. This is the intersection, right? You're asking about the intersection, or what, or the entire thing? Because if I search, I could search the entire thing for. I could search for.
Either the intersection or the whole thing. This is an interesting thing to do.
Okay, let's do
Don't
it
get me wrong,
quickly. Let's
of
do it
course.
quickly because I mean this is just
Yeah.
vertex list of combined rewrite multi-way. So this is the list of all the vertices. Now all I have to do is to remember how to write the function that actually, because I have it embedded. So motive position. Is this? I think motif arc position is going to do it. Let's see. May not. My functions are too. I think they are too specialized for the exactly the Boolean operators. But I mean, this should be quite easy. Let me see. Motif position. Oh no, this should do actually. Let me see. Expression. No, wait. Yeah, I have to combine two functions. Let me copy. It's so frustrating. My functions are too specialized. I can just copy paste and apply them. So this thing will give me all the positions. And when I have all the positions,
Well, for the interest of time,
Yeah.
this could just, you can obviously do this at some other point. I think the key thing to discuss while the three of us are still on this call is the question of, is to discuss Nick's suggestion about searching these other intermediate steps and their corresponding truth tables.
yeah.
So I still don't fully understand the suggestion, I must admit.
Okay, let
So
me
Nick,
phrase
can you-
it. Let me phrase it in case.
Yeah, okay, Carlos.
And
go
Nick,
ahead. Yeah.
correct me if I'm wrong. So what I understand that your basic suggestion, I remember you did mention at one point that search for other implementations, other emulations, but I think the one that you're suggesting right now is that for each, instead of just searching for the explicit emulation that we have for each operator, so this association, right? Instead of just this association,
Yes.
I think Nick is suggesting that for each of the keys, we should have the entire vertex list of the multi-way of its evaluations, right?
No, not quite. You don't have to get a key from the start. Your starting position, you have your multi-way system, all the vertices, all the expressions are combinators. Then you extract every sub-expression of those and run it through all the Boolean arguments to get its Boolean table. And then you can immediately say which one of those corresponds to a Boolean function. To which Boolean function?
Hold on. We take some intermediate vertex that's going to have some combinator expression. You're saying then we take the individual sub-expressions, and then, so let's say I fish out some random sub-expression from one of these intermediate steps, and then I feed it true, 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 false, 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 etc. And we see what happens if we just feed those arguments to these kind of sub
Again,
expressions that we fish out from these
basically
intermediate
your
states.
basically your multi-evolution for those known combinators that we searched for provides you like a space for the other search. Instead of enumerating all the combinations that are possible, this just provides you just for the nice subset that you can just search for them explicitly. And you just need a simple function that just given a sub-expression, give me the actual Boolean function that it corresponds to, or missing. It's either corresponds to one of those or it doesn't, right? And if it corresponds to some Boolean function, you just highlight it.
But but do I have the right idea that you would take one of these random sub expressions, you're testing to see if it's a Boolean operator by just feeding it true, 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 false,
Yeah.
false, true, false, false, and seeing what the outputs are. And if
Sure.
it gives okay, and if it gives the same out, so okay, so I happen to fish out. I take some intermediate state. I pick some sub expression, and then I throw a truth table at it. And if it behaves like XOR, if it walks like XOR, if it talks like XOR, if it quacks like XOR, then I'm going to say, okay, this thing is XOR. It's not the one that we have, but we're using the same truth values,
Mhm.
and so it's just an alternative XOR. That
Yeah.
that sounds okay. I like this. Yes,
Yeah,
that's a good
and you do
idea.
it not just for the binary case. You do it maybe up to some number of arguments, and you just say if it's basically you just enumerate its Boolean table. So you just assign an index of a Boolean function that it corresponds to. If it actually evaluates to for each possible Boolean values, it evaluates to Boolean value again, like to true or false.
Do we have, so right now we have the minimal arity to Boolean functions. How's the search going for, I mean, Carlos is Mr. Arity. How is it going for arity 3?
I mean,
No, we can search, we can even enumerate an actual minimal combinator expressions for arity-free Boolean functions. Yeah,
yeah,
that's
Yeah. Have you tried it yet, or is this something that remains to be done?
yeah, that has to be done. At least
Okay.
on my end, I haven't done it explicitly. So I think I can show you your question before we end. If I do. Oof.
What?
Oh,
What is that?
so that's not an error, but it's obviously it's huge, right?
Oh, I see. I see. Yep.
So how do I?
If you say show all, you could it'll be large, but it won't be formatted in that way.
Yeah. Why is it white? Oh, okay, that's why. Right. So the key here is: are there any non-purple hits? Because purple is and we are doing and twice, right? So ands
Yes.
ands should happen. My guess is that they're not going to be, but yeah, nested ands as they should be because we are doing
Yes.
associativity.
Yes. That's how we begin, right?
Yeah. So, oh wow, this is long.
Just to zoom, okay, because we should probably wrap soon.
Yeah,
Just to zoom out, I mean, so one thing, Carlos, is I would say originally we were gonna try and schedule this for the weekend, but it appears as though it's not even like a good time for really anyone. So we should have some kind of formal review maybe early next week, or kind of maybe in the middle of next week. I would say at the moment you're very close to having kind of results that could be packaged up and shared, at least as an indication of early progress. I mean, showing some of the examples that do what you might expect, which is like, where you begin with some initial Boolean expression, and then it just becomes dissolved in these, intermediate combinator expression states. That's to be expected. I would try as hard as you can to find non-trivial examples, and I think Jesus, this is long.
This is super long. I mean, but it's good. It's a good reality check. It's only purple. I think. I mean, there should be, right, because each of the sub-expressions in the nested brackets, and nesting is just putting more brackets on the expression, right? So each of them can be rewritten independently within the brackets. So within the brackets, we're gonna get a copy of what we had before, which was only purple. I mean, it's feasible that the interaction of the two brackets might generate something new, but I think it will be very, very weird if that happened. I think we're halfway. Let me go faster to the beginning.
Just remove this output.
Okay, here we go.
Yeah.
So,
So
yeah.
I mean, I would say kind of as a next step. I mean, doing these small fixes that we've discussed, like fixing the coloring for the multi-way systems, being able to investigate the particular paths for these multi-way systems. These are both kind of obvious things to do.
Mm-hmm.
Continuing what you're doing with the actual axioms of Boolean algebra is also kind of an obvious thing to do. Trying more complicated Boolean expressions, like ones where maybe you have a left hand and a right hand side and equality between them.
But wait,
I mean, just
James,
yeah.
I need to clarify something. Why do we want
Yes.
complicated expressions? What can we gain from complicated expressions? These simple expressions are complex enough that there's phenomena we don't understand already. So I just want to understand, why do we need complicated expressions?
I just want to see if you have something that's like a little. You have a few more operators at play. So you have like maybe and, or, equals. It's a little longer. I just want to see if that provides enough kind of complexity for less trivial behavior to appear in the combinator evaluation. I mean, these are what we're doing already seems quite complicated. Maybe it's not complicated enough. We don't know.
But I mean, I'm just trying to understand. So, how can I know that this is not complicated enough?
We don't. It's just something that's worth checking at some point.
But
It's
what am
like
I checking for?
we don't.
I mean, I'm
No,
asking
what I-
honestly. Like, what is
Well,
like a
my
graph?
point is this. No, my point is this. Right now, using and or, for with just two arguments, we don't find anything interesting when we look at the intermediate states. When we use something like XOR, we find something that's slightly more interesting, right? But what we are investigating is the general combinator emulation of Boolean algebra. And so, within the grander scheme of Boolean algebra, XOR true false, for instance, is super trivial. It's very, very trivial. I mean, these are, so having something where
Wait,
it's an actual
we don't
Boolean
know that, right? We don't know that.
We don't know, but it's still, quite elementary.
I mean, but that's
At some point we will look at more complicated versions of these. I mean, this is a natural thing to
what
consider,
I'm
right?
trying to say is that complicated on one side is just our bias. It's our human perception bias to say, oh, this is more complicated on this side, because XOR turned out to be quite complex on the combinator side, whereas and equals was also quite complicated, whereas and was very simple. However, XOR and AND are completely indistinguishable in terms of complexity, quote unquote, on the Boolean side, right? So,
But even in my own investigations, I started looking at ones where you have a left-hand side and a right-hand side inequality. And I mean, those are quite complicated. I mean, even the Boolean, or sorry, the combinator emulation of those. I mean, the combinators themselves are quite complicated. The more, the longer the combinator is, the more ways it can be rewritten. And I mean, this is kind of a silly debate to have.
I get the point that the rewrite system is going to be much bigger, but I think that we are observing. So the thing is, we are observing phenomena at the smallest level, which we can go smaller than this, right? Because these are just the evaluations, and at the smallest level, we are seeing some phenomena that's interesting enough that we don't understand, right? We still don't know to what degree the things that happen in between the evaluations from other evaluations are related or not. We still don't know if in this, for example, in this associativity property of and twice, if this intersection here in the middle is saying something about, the fact that they both are confluent, right? I mean, this is the interaction of two independent multi-way or otherwise independent multi-way systems, right? These are kind of and these things are very complicated already, right? And these are the smallest expressions. They don't look fancy to say and true false, right? Like that doesn't look very fancy. But at the combinator level, the phenomena of the sort of graph theoretic and sort of just rewrite system theoretic phenomena that's going on, it's very complex, right? So I mean, we can render some of the multi-ways of the longer ones. I mean, that cost me nothing to just render some of the longer ones. What I'm trying to say is that probably developing a good sort of charting intuition of the simplest, smallest possible phenomena, which are non-trivial, because I mean there are some that do look trivial, the ones that we saw at the beginning, but there are some that do look non-trivial. I think it's important to then extrapolate and do big number analysis and things like that. But just as a general point, I guess, because otherwise, I mean, we can render big stuff and compute big numbers of however many times this happens and histograms and whatnot. But I think that this is close enough to the foundations, and hence the name, right? It's Sub-Axiomatic foundations. We're close enough to the foundations that we can go step by step, saying, okay, so when the system is confluent and it has several initial states and they all end up in the same. I mean, this is just some graph theoretic stuff that we have to do, right? And it looks very complex for graph theory already. These are big graphs, and these are non-trivial things that are happening within graphs.
I'm not suggesting that we consider more complicated Boolean expressions for the multi-way properties. It's actually just because so far I haven't seen intermediate steps when you actually evaluate particular paths and you highlight the presence of Boolean operators in the intermediate steps. I haven't seen anything, really mind-blowing. I mean, even with the XOR case.
What would be mind-blowing? What would be mind-blowing? Because if I see something that looks like this, right, like an orange that pops up in the middle of evaluating NAND, and orange is whatever, not converse or implies. This to me is okay. Sure, these ones are not the ones happening spontaneously, but the ones that did happen spontaneously, like this one, right, like falls in the middle of converse or whatever.
Yeah, but it's just one. I mean, look, it could be the case when these get more complicated that you have more things that pop up. They pop up and they stay for longer. They, right now, if I just see the presence of kind of one that happens to pop up and then disappears, I still have reservations about whether or not I'm going to attribute any mathematical significance to that, or whether or not it happens to match something that's a Boolean operator, but it's just a contingency.
But James,
I'm not sure.
Okay, so there's something I don't understand about your perspective here, because I mean, these are the smallest combinator emulations within this emulation framework, right? There might be others, and we should explore the possibilities of changing emulation and whatnot. But having fixed this emulation, these 16 Boolean functions emulated this way, these evaluations, these are the smallest possible paths, right? So so the point is, in a way, there's nothing else that can really happen if all we do is make larger expressions of these guys, right? Like it's going to be combinations of these, and it's going to be, I mean, if you want to start to see patterns at the very large numbers, then sure, I agree. We could start running like very large experiments, But I think that becomes sort of statistical mechanics approach to this stuff, and that's fine. I'm not saying that's not interesting. I'm just saying that it's quite different from trying to understand, if implies happens in converse, then what does that mean? Something that do we have to find, this kind of, because you say that this is once and it could be by coincidence, but I don't understand what that means, because this is what it is. It's not coincidence. It is that because that's what it's supposed to be, right? It just happens there, and the question is, does that mean something or not? It's not whether because it's one it looks kind of coincidence, and it's there. That's a fact. And the question is, does that mean something beyond than just matching the pattern or not? And I don't think that.
Well, that's
going
no,
larger.
we're saying the same. We're saying the same thing. When I say it's a coincidence, what I mean is, does it have mathematical significance or not? Obviously, yes. This is exactly, we do get that particular intermediate state when we evaluate it. And this is, as you say, we are evaluating these particular emulations of these operators. And so even when we consider larger expressions, the evaluations are still going to contain the evaluations of individual operators. So it will also contain, evaluations at particular sub-expressions of these larger. It'll contain evaluations of sub-expressions of these combinator emulations of these larger Boolean expressions, and some of those subpositions might be novel. It might be the case that you have. So that is part of it, which is it's not just like in the Boolean case where you'll decompose it purely into the individual operators. It'll be you'll be able to evaluate it at these different S and K positions, and so I do suspect that there will be novelty when you actually evaluate these emulations of these larger expressions. But we're saying the same thing about this, about our lone orange friend here, which is it pops up, but is it the case that it just so happens? Look, the point is, yes, it matches this particular minimal Boolean operator. The question is, when I say it's a coincidence, it matches it, but if we have a long expression, it could be the case that we have these intermediate states that have subpositions that match the Boolean operators. Whether or not there's any mathematical significance to it remains to be determined.
Yeah. I agree. I was just not fully getting what you meant, but I agree. I think we should explore that. I'm particularly fond of this idea that if you take this axiom, what is it here? If you take this axiom in this particular evaluation, what I find interesting is that you're going to have, essentially all the possible evaluations of these are two ternary Boolean operators, right? Each of them different. The thing is, they happen to be equal because that's how Boolean algebra behaves.
Because they evaluate to the same fixed point.
Yeah, well, not only that, but that for all arguments, right?
Yes.
So
and you could make that multi-way system too, actually.
Yeah, but this is exactly what I was saying the first week, right? The first time we started is that you have the multi-way of the actual Boolean algebra axiomatically as a rewrite system on itself, and you will somehow project that rewrite system onto the combinator one, and to what degree that is preserved, that's still an open question, right? So what I was trying to say is that what I find interesting is that there is a property of the multi-way system. Once you write something like this, like the evaluation of associativity for AND, you have, if you want to say something about this, you can essentially either list explicitly all the states and say something completely granular about states, as we were saying before, or you say something topological about the multi-way graphs that they follow. Something along the lines of, look, they all belong to a larger graph which has this initial states. It's no longer one single initial state, but it's this collection of initial states, and they all have. This is a non-trivial fact, right? This graph here is a confluent graph, right? It's a confluent directed graph, whatever. So that's a non-trivial fact, graph theoretically, right? So what I'm trying to say is that we could possibly attempt to characterize the phenomena like associativity for and, but also more complicated, in some at some level of graph theory for the multi-way system, where the states are irrelevant, and therefore it will be much better for then transporting that to any other context, because then it doesn't really matter that it's combinators. It's just, it's a property of the multi-way system. It's not a property of the fact that S and Ks do whatever. So
what kind of graph topological properties do you have in mind?
So confluence, I think confluence is the obvious one. Confluence is screaming out loud here, right? So this is it looks very complex as a graph, but this is confluent, and it has two initial states and it's confluent. That is a very special graph, right? Not many graphs satisfy that condition if you just throw random graphs of this size.
Well, but it'll be the case that if you take any Boolean expression that evaluates to false, you take any other Boolean expression that evaluates to false, and you union them, you will get something like this.
No.
Where they're confluent.
Yes, I agree, but they wouldn't necessarily intersect non-trivially, right? And these do. Those are the yellow dots are the intersection, right? So what I'm trying to say is that imagine that you don't know anything about Boolean algebra. You don't know anything about associativity of and or anything like that. But you know about combinators, and you happen to choose. I'm seeing two states here. You should really think of however many. What is it? 2 times 3 or what? 3 choose 2, whatever that is. 6 or 9 or whatever it is. Combinations of arguments, right? So these are all initial states. These are initial states that you put on your Combinator emulator, and then they all flow. And because we know this is true, they're all going to converge to false. And we know we just took 2 of them, which is this right hand side and this left hand side, right?
Yes.
And they happen to not only converge to false, because we know that, they actually overlap on the way. So if you think of all the possibilities, this is a big multi-way system with several initial states that all have one final state. So that entire multi-way graph, that object is formally equivalent to the axiom of associativity of and.
Yes, I get that. But what is the significance of the states that they share?
Well, it's not the states, but I would say is the topology. That's exactly the point I'm trying to make.
No. I mean these yellow vertices.
Yeah. The fact that there are some particular states, I'm trying to diminish the relevance of the particular states. What I'm trying to say is that if you squint and you just look at the topology of the multi-way graph, right? There might be, this is a conjecture, we don't know, but it might be that the axiom of associativity for and, because the literal data that the Combinator emulation gives us for the associativity property of and is the entire multi-way, including state labels, the actual states of all the possible initial conditions, right? So my point is that that's just a statement of fact, right? There's no content there. What I'm saying is, maybe if you actually forget about the states and just topologically just take your graph as a graph and not as a label graph, then there might be properties that you can spot there, and it might be possible that within all the graphs that are generated within the Combinator realm, these are all non-isomorphic and they are actually distinct within. Well,
that'll be really cool. Yeah.
That's
yes. I mean, look, in this crazy multi-way world of ours, we're always looking for these higher topological signatures that give us some reducibility over these and help us to classify.
Exactly.
No, but my kind of provocation though, right? Which is, what if it's the case that I take two different Combinator emulations of Boolean expressions that both happen to evaluate to false, and what if you try that with a bunch of examples, and what if those ones also have instances where they intersect at common states?
You have to discover that.
If that's the case, then it diminishes the special significance of this one, unless you're saying that it's not the fact that they intersect in general, but there's some other other property of this particular graph that makes it seem you can classify?
I mean, I was being quite precise by saying the topology. I don't mean the fact that they intersect, because that's us reading some states with some criteria. It's the actual topology, meaning these are graphs, they are what they are. So the actual topology of the graph might be different, might be not. I mean, we have to discover this. What I'm trying to say is that the same way that we've scrutinized the evaluations for simply the operators themselves, true, false, true, false, true, false, false, true, true, I think there's quite a lot of value in. I mean, that hasn't finished yet. I have to finish that direction. So after that, I think the natural thing to do is to go to the ternary ones and do a similar game to gain some sort of induction steps, and then maybe yes, okay, let's blow it up and let's consider general ones and keep it running for 2 days and see what it spits out and whatnot. But I think there is the chance that we can actually, recognize some phenomena here. And I mean, we're agreeing. I'm just relaying the same thing. It's not that I think we disagree on anything. But
well, I guess okay, the one concern that I have, right, is that you said that the key graph theoretic property here is confluence. And the only point that I'll make is that if we're dealing in combinator emulations of Boolean expressions, they can only evaluate to one of two fixed points. And so they're either going to evaluate, if you take two random Boolean expressions, you're either going to, if you try and union them, you either find that there are two separate sinks, or that it's confluent to the same fixed point. And so it obviously can't just be that, because that's going to be the same for, I mean, those are the two outcomes no matter what. So it has to be the case that if there are graph theoretic properties that are more distinct, that it's not just confluence, but it's also not just the fact that there's an intersection, because I don't have any reason to suppose that the intersection is unique either. So then there are some. That's why I said
topology.
Yeah.
That's why I said topology. Topology is the topology of the graph. I mean, it's what it is.
I mean, if it's the number of holes in the graph or something,
It's the graph itself. What I'm trying to say is the graph itself. The graph is the information itself. I mean, it has less information than the SK Combinator rewrite, because you are forgetting about the states, but still has a fair amount of discrete information, which is the topology of the graph. Right.
Nick, do you have any views about this?
I mean, it's just a suggestion. It's not even.
Nick, by the way, there's a very scary shadow in your background. It looks like
This one?
Yeah, what is that?
Well, this is the treadmill. I'm camping under my treadmill.
Oh, I see.
Oh, you ran upside down. That's interesting.
Well, it's not in the actual running shape. It lowers down and then.
Oh, I see. Because it's blurry, it just looks like some,
menacing figure.
Yes, it looks like some weird shadow in the background. Okay, fine. Well,
all right, good.
I mean, look, I think the most sincere thing I can say about this is it's good in general with multi-computational modeling to search for graph theoretical, topological, etc. signatures that give you some degree of reducibility over these. And, on the one hand, I think I mentioned this like very early on, right? On the one hand, we want to actually inspect the content of these intermediate steps in these evaluations in order to understand to what degree, we are retaining our emulation of Boolean algebra, and to what extent we're basically just descending into combinator machine land before finally evaluating the next point. That's one question. And yes, the other question is, once we're doing Boolean algebra at this combinator level, especially once we're doing it at a sub-axiomatic level, it is so messy. It's so computationally, multi-computationally. I don't want to say it's irreducible, because you kind of know that's going to tend towards a fixed point, but the structure of it is quite hairy. And trying to have some new ontologies for this that are at the combinator level, but nonetheless give you some reducible abstraction, lend you some kind of reducible purchase. That yes, those are desirable.
Yeah. I will try to, because
And
this,
it, and,
this
it, and if it's mostly a kind of a speculative instinct, like, hey, we should be able to study these things topologically, then of course I'm not going to disagree.
yeah.
But but
It was
I
just
think we can agree. We could probably agree. We have no idea really topologically what. Okay. That's fine.
Yeah.
This is a kind of a provocation on Carlos's part. We should I think this is a good thing to say, right? Which is basically we have these multi-way graphs, and we're not studying them graphically. This is something that we should do because maybe there's some abstraction that we can gain from that. Yeah.
I mean, I was just making one very general point that it's not that I had a clear idea of what next week or next time.
Okay.
I will express it, but I was just saying that in the same way that on the Boolean side, true and false evaluates to false, the topology there is two vertices on one edge, right? One state, edge, evaluation, one state, right? There's no topology there. However, on our side, we have something that looks like this. Okay, this is for the bigger one, but we have some graph that has some topology. Obviously, we have the entire rewrite system. That's the full data. But the next sort of coarse grain of the data is just the multi-way.
Exactly.
Right? So that's what I was meaning, that we have now this extra thing that we can hopefully use as handle at some point.
I agree. Yes. Well, okay. We went like 45 minutes. Yeah, that's okay. There's a lot to discuss here.
Yeah.
Okay, so just to kind of review before we wrap, what are the next things that you're gonna do, Carlos?
Okay. So I'm gonna bring the functionality hopefully to the final stage where it does exactly what we want. I'm also going to. This is very adapted to Boolean evaluation now, so I'm gonna do it for expressions in general, that not necessarily just the pairwise evaluations, and. So I'm gonna work on that, and I'm gonna try to implement Nick's idea of checking for all the possible patterns, and I mean I'll work with him because I want to fully understand, because I don't know if I understood 100% what exactly you meant, but we'll work together. I mean, we've worked every day together anyway, so I think it'll be
cool.
Fine.
Yeah, I think if I understand, it's just you're kind of fishing out possible Boolean operators from these intermediate steps, and you're throwing truth tables at them by giving them, true, false arguments, and you're seeing if it happens to match these minimal Boolean operators that we have. So something like that.
Yeah.
Yeah. Okay. Well, cool. Well, yeah. I mean, I would say that. Let me just think for a second. We have these kind of rotation cycles for these different meetings. It feels like it's been a long time since we had a Sub-Axiomatic Foundations meeting, and so it could have been that I don't remember when we met last week, but we should have another meeting. I would say kind of maybe earlier in the week.
Yeah, I agree.
What I'd kind of like to do is to meet with you, Łukasz, Nick, and just kind of produce a summary of what we've done so far. I think basically all of you guys have these like sprawling notebooks, kind of piecing together the kind of greatest hits so far into a kind of a simpler notebook, and doing some kind of synthesis of what's been done so far and what remains to be done. And then we can pull some other people in, and we can have like a basic review of what's been done so far and brainstorm next steps. So that's what I have in mind for this upcoming week.
Yeah, just a reminder that I'll be flying Thursday night.
Yep. Well, we should probably be able to do it before you go.
Yeah, I think we should do it before I go. Yeah, for sure.
Yeah. All right, cool guys. All right.
Sounds great.
Yeah, it's coming along. This, if you don't mind sharing the notebook, I kind of like to play around with this too. It's good that we have some kind of general functions that we can now, like, they seem general and we can apply them to different examples. And so, yeah, there are some things to patch up. I think that Nick's suggestion about search is well taken. It'll be interesting to see after having made those searches if other things do appear. If they do appear, then then there'll be less unintelligible combinator content and more Boolean content, which is interesting.
Indeed.
We don't know. Maybe there won't be anything. Maybe there will. This is what makes it appropriate for experimental study. All right, guys.
Indeed.
Well, cool. We'll chat offline and we'll continue to coordinate. Anyway, cool. All right. See you guys later. And for the audience, thanks for watching. Again, this is very much a kind of new experimental area in multi-computation and metamathematics, et cetera. So if you have questions that you want to ask in public or in private, you can visit our Discord page. We do have a channel that's designed particularly for you to ask questions, and we provide answers as well. If you want to message us privately on Discord, you can do that as well. All right, guys. Cool.
Yep.
See you later.
Have a good
Cheers.
weekend.
Take care.
Goodbye, everyone.